Okay, so chapter 7, we continue with chapter 6. So chapter 6, you have seen how to calculate the concentration at a certain depth. Then today we look at what happened at the macro scale when you heaten or you do the things. So just recap chapter 6. You have a ratio, concentration ratio. Concentration ratio. E ratio here equal to ERF Z. Then there's one more equation, D equal to B something, to substitute back here. Okay. So chapter 7, we look at strengthening mechanism, more on the mechanical parts, more on the mechanical method. Chapter 6 is more on the chemistry strengthening, where you do carburization. You put carbon, oxygen, or something on the surface, then it will go inside the material. Okay. So chapter 7 is more on a mechanical way. You roll it, you pull it. So recap, previously we have two type of impurity. One is substitutional, where you substitute the host sphere or host atom with impurity or external entity. In this case, you see the green color ball here. This is a substitutional impurity. So substitutional, it must comply or follow the Holmes rules. There's a Holmes rules. So need to go and read. If you don't know what is Holmes rules, it's actually mentioned there is a certain guidelines. For example, the radius, you should stay within how many percent, the electron valence, the electron negativity, and all this. Go and read. Then another type of impurity is interstitial. You go to the space there and you park there. Okay. So this one usually will ask you interstitial using the crystal structure or unit crystal structure to find the gap between the sphere. And from there, we'll ask you atomic packing factor for the interstitial impurity question. Okay. So again, previous class we mentioned the word solute and solvent. Okay. Solute is the one that you add inside the host. The host is called solvent. Okay, the rest you read lah. Okay. Either both, for example, substitutional, if it's too big, too small is no issue, but too small, you will create movement around the space there. If the green color sphere here is too big, you're going to push the surrounding sphere. When you push surrounding sphere, you will create stress. Same with this orange color dot here. It's a interstitial impurity. If you put in too big, you're also pushing around the sphere around it, so it will create stress. Okay, that is not what we want. Okay, then on mechanical explanation, on strengthening, when you put in all this impurity, it either is interstitial or substitutional. The main purpose is to stop the movement, is to resist the movement, because you add in more things in the space there, so that it makes the host or you make the solvent harder to move around. That is on the mechanical perspective. Why or how you strengthen the metals. We are now at the metals. look at metals. So strengthening, you are actually adding something in, or you substitute the something inside there to stop the movement. To stop the movement, or movement, yeah, two way. Either you fill out the space, or you fill in the vacancy. You fill in the pothole there. Okay, there are two ways. Okay. So this one is a solution, solid solution strengthening metals. This one you add in impurity to increase tensile and yield strength. So there are three graphs. So the first one is tensile strength. Okay, tensile strength versus percentage of nickel in WT, weight percentage. All right. So by now you should understand what is tensile strength, because this question going to come out next week. If you don't understand, go and study. Weight percentage, also go and study. All right. Then this one is yield strength. Yield strength is different when you increase the impurity. Okay. So this yield strength we are using, it can be 0.1%, 0.2%, 0.3%, depend on the country or the question asks you to set. Okay, so this one is the elongation versus this one is percentage. Percentage. So elongation is a ratio. You can put in ratio. And this graph is in the percentage. You multiply 100, right, versus nickel. So as you can see here, if you add in impurity, the tensile strength increase. You add in nickel content, yield stress or yield strength increase. However, in elongation dimension or elongation axis, you add more impurity, elongation will drop because you stop the movement already, or resist the movement. Okay. This one we call it ductility. Elongation also means ductility percentage. So if you add in impurity, you make the thing stronger, but actually when you use the word strong means it's very hard to pull already. So ductility drop or elongation drop. Okay. So this is more look into the molecular dimension. So what happened if you put in impurity atoms? So if you look at the this diagram, so this orange color impurity sphere here is a smaller compared to the surrounding host or solvent. This is solute, this is solvent. So if there is a gap, then there is a minor movement. If any mechanical properties or stress, external stress acting on it, on the metal. So you'll see the orange color will pressing in. So if you see this diagram, this section here or this small area here will have tensile strain on the surrounding crystal lattice. Okay. Tensile strain means tensile means you're pulling away, the two arrow pointing outside. Strain is a deformation. Okay. So if you have a smaller impurity, it happen tensile strain. However, if you have a larger impurity, like the green color diagram here, it will have impose compressive strain to the surrounding host. So these are the keyword. If we ask you what is the effect of the impurity, the size of the impurity, this one usually is the last section of the question. You calculate the R, or in a table. Okay, the type of question will be, it will start to ask you to calculate, to ask you to draw lattices. either BCC, FCC, or HCP, you draw. Then after that, you calculate its atomic packing factor. Then you calculate, let's say I put, let's say you're having FCC. So these are the space that this is the X that you need to find if the question I set like this, right? So you draw, then you find the A and R, right? The A and the R here. You find the relationship A equal to how many R, okay? Then you find you have the R already, then there's a gap here. So there's an X there. So the X there, then I'll give you a table, material. So copper, nickel, carbon, and so on. You're having the radius of the copper, carbon, and all this. So the question section C will ask you from the table which one will what? Which one will have compressive strain to the surrounding, will have tensile strain to surrounding. You explain. Let's say you calculate, okay, you suggest, this one is carbon. So you go to the table, carbon, then you explain why this carbon, when you use carbon, what happened to the, what is the effect to the surrounding host? Either is tensile strain or compressive strain. You need to answer something like this. Means the third part of the question usually asks you to explain things, explain why, and all this. Okay, so this slide is important, especially for section C kind of question. Okay, the rest you read. Okay. Now previously we learned about the defect edge dislocation, which is you see the inverted T. So inverted T means at this section here, after this section, there is a hole there. There's a discontinuity of the host molecule or sphere. So there's a space there. So if you have a space there, you need to fill in the hole. So you can fill in by two ways, either substitutional impurity or interstitial impurity. If you use interstitial impurity, you need to use a lot more impurity compared to the substitutional impurity. Okay, so there is a space there that you can calculate what is the volume of this space here, right? Then from the table of molecule or element, for example, carbon, nickel, you have the radius. So then maybe I'll give you the other parameter. You should able to calculate how many atoms can be filled inside here. Okay. So these are the other things lah. Things. This is another way of writing. Means resistant to movement. It just tell you this red color box here. It just tell you what happened. You put in impurity atoms. Okay. So this one, it will tell you when you do solid solution strengthening, solid solid solution strengthening, we look at metals. So there are two things that you need to consider. One is relative size and short range order. These are the two. So short range order more on the bonding, one on the bonding. Okay. Now we go into how we make the metals stronger by mechanical method. So first, we look at co-working. Co-working means you make you do some deformation on the metals at room temperature or a temperature lower than the melting temperature. Okay, so cold working, it means cold relative to melting temperature of the metals. All right. So you have a TM or T melting, let's say 1000 degrees C. If the temperature given is 800, it consider cold working. Let's say the metals you heat up to 800 degrees C. This one, and then you go and hammer it. This one still consider cold working. So when you work on it, there's a deformation happen. You roll it, right? You make a break or something. So there's a deformation happen. You calculate using percentage of co-work equal to area, ratio of area multiply 100. You focus on the original area. Okay, then you calculate on the top here is the changes of area. Right. So percentage of co-work equal to delta A multiply 100. Okay. This tree chart is very popular when it comes to assessment also, or when it comes to test or final exam. So this is the tree chart here. You need to read carefully. Don't use the wrong chart. The first chart is yield strength versus percentage of co-work, which is this one, this equation. Second is a tensile strength versus co-work. Third one is ductility versus co-work. Then you'll see different material here. So don't read the wrong chart. Don't read the wrong color. Okay. Okay. Then this one is another one. Stress versus strain. This is a tensile graph. This one is on low carbon steel, same material. But what happened to the tensile graph if you have solid strengthening mechanism? You see the green line, blue line, and red color line. So if you increase the percentage of work, means you roll it, become shorter or thinner, then you see that the mechanical properties for stress is increasing for metals. For metals. And then later we'll look into microscopic, why when you roll it, why the metal becomes stronger and stronger. Okay, so this one is another strength hardening mechanism. So usually when we load the metals, we load and then we test until it fails. So this is for the normal testing. You load and then you wait until it fails. Another way of making the material stronger, you do co-work. You pull it up to there's two points here. One is U point number 1, U point number 2. You pull until a certain point, you unload it, so the load will drop. It will drop. So actually the metal already elongate a bit already, and reach a plastic region already. So it's like you pull, you let go, it still go back a little bit, still go back a little bit at this region. Then you load them again on here. Okay, so this one is strain hardening mechanism you on the stress strain diagram. Means how you make the metal stronger, or you call it pre-stress. So you pull it and you let go. So you store some energy inside the material, then you apply it in the operation. Okay, now we look at copper and zinc alloy. Alloy means you mix two metal together, alloy. Okay, so let's say we mix 70% copper, 30% zinc. And you're seeing the two graph here. One is tensile strength and yield strength. So black color one is yield strength. Blue color, light blue is tensile strength, and a little bit dark blue is elongation. And the one on the right also same. The differences here is in the oxygen-free copper. Another one is in the 70-30 percentage. Same y-axis, same x-axis. But you see the differences between left and right. The left one is unalloyed oxygen-free copper. So you'll see this one on the left is copper properties. You see copper properties is a bit lower compared to the alloy. Although on the left you see is a bit higher. However, you see the reading on the left maximum is 60. On the right maximum is 120. So don't read the wrong graph. Don't fool by the size of the graph. Okay. This will be the trick that usually will use in the test or final exam. Sometimes we purposely pull the graph in the same size, but we change the scale. So look carefully when it comes to test or final exam. Okay. So on the left to right, if you do alloying, you see the properties increase. Right, the properties increase. Press you read now. So this one. Okay, so this one, when you read 30% co-work, 30% co-work, what I mean by 30%? There's a change of 30% of the area. Okay. The formula will be this one. AO minus AD. Why you take original minus deform after deformation? Because when you pull metal, area will shrink. Area will shrink. If you take deformation minus original, you get negative value. Then you get the wrong answer. So if you look at 30% co-work, the tensile strength will be around 48 the value will be 48. This one is imperial unit, but at this point, unit doesn't important because we are comparing the same unit left and right. So you look at the right-hand side, you see 30%, the tensile strength become about 70. Okay. Okay, look at exercise. Compute the tensile strength and ductility of a cylindrical copper rod if it's co-work such that the diameter is reduced from something to something. Okay, so can you calculate the percentage of co-work? What is the value? How many percent? So how many percent co-work? How many percent? How many percent you get? Oh, how many you get? Huh? 19.74. Okay. So you have the percentage already. So you compute the tensile strength and ductility of the cylinder for copper rod. This is a copper rod. They given you diameter. You need to show this one. How you get 19? How you get 19.74? This is how you calculate area. Practice. Every time I ask you to calculate something, please practice. I've seen someone fail this module because he have careless mistakes in calculating the area. Any question for this one? You should get 35.6%. Of course, you can use pi r square if you want. This is diameter. Okay. Then you need this graph. The question asks you tensile strength. Which graph you should use? Huh? Which one? Left, center, right? Left, sorry, center. He asks you tensile strength, go to tensile strength. You read yield strength wrong. So you get 35.6. You go to the graph, you go and find where is 35.6. Or roughly 36. So here, if you draw in the middle, I give you wrong answer. If you show your answer is about center, I give you wrong answer. It should be a little bit to the right to show 36%. Then you draw a dotted line. You draw the dotted line. So this answer 35.6. Then you draw a line. This one is copper. You need to extend to the left. There's one value there. So 35.6. You extend to the left. This one is in megapascal. So 36 to the left is about less than 350 megapascal. Okay. And it asks you the ductility also. It asks you the ductility. So ductility is over here. 35.6 copper to the left, less than 10%. Okay. So this one will have one value here. This calculation, 2 marks. This line, 1 mark. This value, 1 mark. This value, 1 mark. If you don't do anything on the graph, 0 mark. Usually this chapter 7 question, you need to detach the graph and stapler together with the question. Okay, just don't read the wrong graph lah for this module. Okay. You can draw anything you like on the yield strength graph. There's no mark given. But it will help you in other segment of the question. Because you have learned how to calculate yield strength, you know how to calculate tensile strength, you know how to calculate elongation. All right, don't confuse cowork with percentage of elongation. Okay, so you should be able to differentiate tensile strength and yield strength. Okay, how this graph link to your question? In chapter 5 or chapter 7, there's one question asked, give you safety factor, design safety factor, or factor of safety. Right? So you need to careful use the correct graph. Now look at how the recovery and deformation happen. So there are 3 phases when you are plastically deform the metals. So you have recovery stage, recrystallization stage, and grain growth stage. All right. So if you look at this graph is also important. So how you read this graph? You forget about the one on the top. You look at the diagram over here. So here, this graph, the x-axis is the increase of temperature. So you can start from maybe from room temperature, then you continue to increase the temperature. So this is the grain size of the metals. So if you work at the room temperature, you do recovery. Means this one here, you co-work and recover. You roll it, you pull it. So then it's in the recovery stage. Recovery stage, you're still seeing the normal grain, the grain boundaries, all this still there. But then you increase the temperature. Okay, you increase the temperature. Something happens, something start to grow within the space here. It's like chicken pox already. So small grain will grow. Then you need to label new grain inside this diagram. You draw all this line, this hairline, big one. Then after this diagram, when you increase the temperature, a small grain will grow. And you further increase the temperature, the structure will, the grain will grow. Right? You learn about nucleation, all these things. You increase the temperature, it will start to grow, and it will change from the left-hand diagram to right-hand diagram. Then after you look at the microscopic changes, you look at the mechanical properties. So you have strength, you have hardness, you have ductility. So you know that when you increase temperature to the metals, you start to melt the temperature already. Ductility start to increase. Okay, ductility start to increase because you increase temperature. You give energy to the element, start to vibrate. Then it start to behave like bubble gum. Then the hardness also drop because ductility increase, hardness also drop. Strength will drop. Okay, why strength drop when you increase temperature? Because of the small grain here. Small grain actually is you create a weakness or defect to the structure. Then on the top is internal residual stress. Internal residual stress, why it start from the positive value? Because you roll it, you give it stress. So there's a positive value. But if you increase temperature, the increased temperature, you give energy, the elements start to vibrate and it start to loosen up. So the stress is de-stressed and then becomes zero. The reheating treatment to make the metal soft is called annealing. It's called annealing. So some textbook they use partial annealing and full annealing. This one depend on how soft you do lah. Okay. Important is this diagram. What happen when you co-work it? What happen if you increase the temperature? Then what happen to the microstructure? New grain grow. We call it new grain grow means we call it recrystallization process. Okay, so this one you co-work it before you reheat. So this is like you do roller, then you push in the metals in. So you see the changes of microstructure, the grain, big grain becomes small grain. So you'll see something like this, it becomes straight. And this one you read. Now, recovery is when your cold work metal is heated in the recovery temperature range, just below the recrystallization temperature range. This section you focus on plastically deformed metals, recovery and recrystallization of plastically deformed metals. So there are three phrases: recovery, recrystallization, right? And what are crystallization and grain growth. Grain growth. There are three phrases. Yeah. This one at here. This one is no, this one cowork is at before you reach plastics. Before you reach plastics. This one, this three word is you need this one is for plastic deformed metals. Mean when you pull it, what happened to the material? What happened to the material? And you heat it up, what happened? Right? This one is a normal one. It's a normal one, like what you calculate. The percentage of cowork is these slides at room temperature or temperature below melting temperature. You use this formula. Okay. So okay. This you see the strain. This you cover and recover. This one is it go up a little bit lah. Actually, it should go up a little bit, then it drop. But this is a illustration for it. This one for info. Now, what happen if you heating the cold metals to a high temperature? So this one is a lower temperature. Then you increase the temperature. Something new grain will grow. So during new grain, the phrase is called recrystallization. So when you recrystallization, new strain-free grains will be created or nucleated in the recovered metal structure and begin to grow and form recrystallized structure. This one like you work out lah, you growing muscles muscle cells, right? So you see from microstructure under microscope, this one is during cold work. You roll it, you straighten out the grain, then you start to increase the temperature. You increase temperature, something like chicken pox will grow along the grain line. So you see the chicken pox start to pop up. Then after recrystallization will be the grain growth phase. So all these dark color region will grow. Okay, so this is a textbook definition for recrystallization. Okay, you go and read lah. Okay, then this one will grow as you see. Okay, so there are mechanism there. So mechanism, you have primary recrystallization based on two principles. One is isolated nucleus can expand with deformed grain. So this one isolated nucleus means something, for example, this isolated grain here. So it will expand with the deformed grain. So it will expand. It will become bigger and join with this line here. Or the original high angle grain boundaries can migrate into a more high deformed region of the metals. So this one is isolated. This one means the grain is happen on the line. It's happen on the line, so it will expand the grain boundaries. So it happen on the line here. So you expand and then go deeper. So the rest is from the graph. Okay, you see ductility increase during recrystallization because new grain was there. So it's the rest you see. This one is for copper zinc recrystallization. Increase temperature, drop tensile strength, drop elongation, increase. Okay, the rest you read. Okay, this one is another diagram. Another diagram with the temperature. Annealing means you do heat treatment. Then this is more colorful, recovery, recrystallization, grain growth. What happened to the tensile strength, ductility? Okay, so when you do revision, you take this one as your revision material. So I want to highlight the bottom, this one, the grain size here. Grain size only appeared on the graph during the recrystallization stage. So here, grain size, you start to see the grain size increase during the grain growth or in the recrystallization phase. It start to have new grain, then it start to grow. So this one, in this table, it gives you recrystallization temperature and melting temperature. So these are the industry process. Industry process, you got input and output, heat it up, then pull, and so on. So what is that? So another information is important factor that affect these phrases visualization are these 5 points here. Amount of deformation before it enter into recrystallization or what happened in the recovery stage. Temperature, time, initial grain size, and composition. So this one you read. Following generalization can make what happened inside there. So also you read for your info. Okay, so this one you read, there are 6. What I want you to look at is example 2. So example 2 is application of this formula, Arrhenius rate equation or time to recrystallization is CE power Q divided by RT. So it gives you a time if it takes so many minutes to recrystallize a piece of copper at 88 degrees C and 200 minutes at 135 C, 135 Celsius. Okay, so you're given two scenario. At the 8, you get this time. 135, you get this time. What is the activation energy for the process? It asks you to find the Q value in this equation. Assume process obey Arrhenius equation. R is given, T is in Kelvin. So you just do substitution, convert the temperature into Kelvin. Okay, so you have all this equation. T1 equal to CE exponential QRT. Substitute the time, substitute the T. R, if you want, you substitute, you can substitute. Okay, you have two equation. Then you divide two equation. You'll get this kind of answer. When you divide this one, you get this exponential answer. Right? Then you do mathematics, you ln it, you remove the exponential, you have ln, then you have only one unknown there. Okay. Yeah, so you take this one, divide this one, you cancel the C, you have the exponential. Exponential divide is minus. If you don't understand this one, go and ask your mathematics lecturer. The answer is Q equal to something like this. Okay, example 3 is a final exam question standard. We go through example 3, then we end the class. No break, just end the class and see you next week. Right? So you're given a scenario. A cylindrical rod, a no cold brass having initial diameter of 6.4 diameter is to be cold work. You see the word cold work in the question already, you need to write this equation. Percentage of cold work equal changes of area divided by original area. You're given diameter, so remember, calculate correctly, is pi r square or pi d square divided 4. Right? To be cold by drawing means you pull it, such that cross-section area is reduced. It's required to have a cold work yield strength. This is a design problem. Customer, he want a product with at least yield strength 345 megapascal. Ductility cannot access 20% elongation. So customer say, I want this. So you need to design the scenario. In addition to a final diameter of this one is necessary. So customer give you a purchase order. I want this one with this spec. Describe the manner which this procedure may carry out. You need to come up with the procedure and then you send to the production floor. Hey, you need to follow step 1, do what, step 2, do what. Okay, so this one, before you solve this one, you need in your mind, you should call up percentage of cold work equation. And then you are given the final diameter is given. So you have to play around with the chart, So here, something hidden here is that it didn't tell you what is your internal process. You are free to choose your internal process. Okay, so the procedure here. So you calculate. The original is 6.4%, 6.4 mm. So you put in original there. Then the customer want 5.1 mm. You put in the calculation. The percentage of cold work from original to final products dimension is 36.5%. You calculate this one. Then you take this one, go into the graph, and see whether you can meet the process or not. Okay, so 35.6 of 36%. So it's about here. So if you extend all this line and then push to the left, you get one value there. Okay, so for example, if you have 36%, you extend up, this one is brass. Brass is orange color. So yield strength is about 400. The customer want what? Yield strength at least 345, which is good because customer want at least. And now you 36%, you give 400, which is good. Okay. Then you go to the tensile strength. They mention tensile strength. Here doesn't mention, so you can skip this one. Then the ductility 36, brass is about here, less than 10%. Customer want 20%. So you are failed at this stage. So you need to prepare a solution so that you give ductility in excess of 20%, which is here. So on your graph, you'll see the first two lines on the yield strength graph, the vertical and the horizontal line. Here also you will see two lines, horizontal and vertical, and then you write the value to estimate here. So 36 brass will be about 8 or 8%. So in your answer, you write based on 36% core work, the ductility percentage is 8%. And this one do not meet what customer want. Customer want 120%. So 20%, you go to the graph again, 20%, you extend to back from 20%, go to the brass, then drop down, draw arrowhead, point down. You need to have about 20%, about 22 or 23% core work, right? So how you do, huh? So you draw this line. This one is too low. Middle one, this question don't have, but final exam show will ask you about the middle things. So you also need to show the things. So what are the alternative spec to meet this one? Can you come up with a solution? You need to think outside the box. If you still stay inside the question, you won't get answer. You need to think something outside the box. You have problems here. What can you change? The first question asked in your mind, what can you change? How many percentage of core work you need to get 20% ductility? How many percent core work? 20% brass is about 23 lah. 22 or 23%. What is the equation of core work? What can you change? Final, you cannot change. This is what customer want. So you can change this one. This one, customer say, I want this one because final, the final diameter, maybe customer want to fit inside something. So you cannot change. So what you can change is to change parameter inside the equation. So you need to propose. This is actually is a starting point for you to start to think lah. So initial, you calculate or all meet, but it failed. Then you need to think back, hey, what can I change in this case to meet the customer requirement? So in this case, the solution is to change the initial diameter. So initial diameter, you need bigger or smaller? You calculate back, you take this one, 32% put here, rearrange the equation, solve linear equation, then you find the initial area, then convert back to diameter. Okay. So deformation must, wait, okay, so if you have 20, about 20, 20, 20, this one about 23, then you move this, you take this 23 to another chart. Let's just to check if you drop the percentage of co-work, what happened to the yield strength? So you pull 23 here, 23 is about 300 something. The arrow, purple arrow wrong idea. It should be inverted. Here, okay, so this one is from the customer spec. If you customer spec 120, no, customer spec it should be 20 something, 23. So you move 23, go back, go up there, you get about 345. Okay, on my slides, my arrowhead is wrong. It should be pointing backwards. Means you take what you find here, customer 120% elongation, because this fail, this specs fail. So you start from 20%. Location also wrong for my purple arrow. So 20%, you get 20 something. So then you 20 something, you move up, you meet the brass, move to the left, you get 345 megapascal. So 345 Pascal, 345, this one is from the spec from customers. So this is a minimum you can go. It's about 20%. So you can play around. If you then you check 20% co-work to meet this one. So 20% you move up. 20% you move up. It will be more than 20%. So over here, so you can play around 20 to 23% co-work to meet the both requirement here. So this one, the purple color is the customer's requirement. You play around, either you move up or move down. It's okay as long as you show the value. So you write 345 customer spec, move down, you get one value. Then purple color 120%, move there, move up here. So you need to play around 20 to 23%. So in this case, we'll find the middle value. So your answer can be between 20 to 23. Then you propose one value that you think suitable. Usually it's a middle value, just to play safe. So we'll use like 20, maybe 22%. So 22%, you check again whether 22% meet the requirement or not. 22%, you move up, yeah, okay, it meet. Then 22%, you move up, yeah, okay, it meet. Okay. So then you use the value, you use 22%. In the slide, I use 21.5, but if you use 22, still correct. You work back, you get the original diameter is 55.8 mm. So you need to use origin diameter of 5.8 mm rather than 6.4%. Means if the storehouse last semester final exam question, I change a little bit of this example 3. I tell the scenario where there is the in-house storage of, I forget the value of maybe 6.4 mm in the storehouse. So what can you do with that material to meet the customer requirement? So in this case, you find out that you need 5.8 mm diameter. So what you do, you ask the operator, or either there are two ways, either you buy a new rod with 5.8, or you go and cut the material into 5.8, then you go and do co-work. There are two ways. Okay. So the answer for this one is to change the initial diameter from 6.4 to 5.8 before you do the co-work. Okay, and these are the example question. Example question. Okay, your lab start next week. Your lab start next week. Okay, we stop here.